Hi, Calculus 3 students. This is the last part, part 3, on the end of section exercise of section 11.11 concerning Taylor polynomials. So before starting, we have to rebrief the part 1 and part 2. In part 1, what did we do? We had f of x, which is x ln of x. The Taylor series in expanded form looks like this. So this is the first term, second term, third term. And then we have the fourth term here that I'm going to put for convenience. So if you're wondering where that 12 comes from, the fourth derivative is this. So if you evaluate it at 1 and divide by 4 factorial, that's exactly what you get. In the second part, we approximated f of x by t3 of x. So in other words, we took these three parts only. Okay, so this is t3 of x. Okay, on the interval from 0.5 to 1.5. And we saw that the error was smaller or equal, actually. Let me put that equal sign to 1 over 24. How did we get that? Well, why f4 of 0.5? So first of all, we're using Taylor's inequality here. And the reason why this 0.5, okay, so it's the 0.5 that we have here. And it's the place in the interval where the derivative is minimal, right? So it's min at, well, actually it's max. Yeah, this is the place where the derivative is maximal. So the maximal value of the derivative is at 0.5. So that's why we use the 0.5, which is here. Does the 0.5 here mean the same thing? Not really. The 0.5 here is we take the values of x that are at the extreme, because that's what will maximize the bound on the inequality. So you could take either 1.5 or 0.5, but the idea here is that whenever you have 1.5 minus 1, you get 0.5. And it's the same thing if you take the other extreme, 0.5 minus 1 will also be in absolute value 0.5. So that's responsible for the 0.5 that's over here. Okay, now the question on this part is, could we actually have used the alternating series estimation theorem? And then why not? So first of all, question. Is there any advantage in using the alternating series estimation theorem in the sense that does it give us a more precise bound? So let's answer that question first. First of all, what this theorem says is that if the series is alternating, then the error is smaller or equal than B4, which means that it's like it's going to be, in this case, f4 of 1 over 4 factorial. And then we do the same thing. We take like the value of x that creates the largest number over here. So that's going to be 0.5 to the power of 4. Okay, so now what does this give? We have 2 over x cubed. So this gives us 2 over 4 factorial. And then this is going to give us, like the green part, is going to give us 1 over 2 to the power of 3. So there's 1, 2 that cancels. We have 1 over 24, 1 over 4. So, okay, my mental math is probably not very good over here. We have like 100. So yeah, that's 1 over 96. So the point is, if we can, we should, because it usually gives us a more precise bound, right? 1 over 96 is smaller than 1 over 24. So let's put it this way. So if we can, we should. Okay. So in other words, if I ask you to estimate the error and you use Taylor's inequality where you can use the alternating series estimation theorem, I will remove some mark because your bound is more precise than what you think. But the question now is, can we? Okay? And if we look at the sign here, plus, minus, plus. Okay, so first of all, what is the first sign? The first sign is a plus. Okay, so we have like a plus here, then we have a plus, then a minus, then a plus, and you can verify easily with the power rule that it alternates past that point. So the first question is, does it alternate at the beginning? And at the beginning, like, no, you have like plus and plus, but we don't really care because it will not affect the error. The error is only coming from neglecting the last couple of terms. So even if it's not alternating from the start, if it happens to be at some point alternating, you can use the alternating series estimation theorem. However, there's a tricky part in this question. It's that no, the Taylor polynomial is not alternating on the interval, okay? So let's actually say this. This series is, and I will put it eventually alternating for x greater than 1. Okay, now you have to consider the radius of convergence as well, which I believe is 1, so you need to be careful about that. So it's eventually alternating when x is greater than 1 because x minus 1 will be a positive number. So since x minus 1 is greater than 0, okay? However, the series is not alternating when x minus 1 is smaller than 0. And why is that? It's because all of these terms, if x minus 1 is smaller than 0, all of the terms will end up being positive. So I will write that down. But this series is not alternating when x is smaller than 1. So, and this is because x minus 1 is smaller than 0. So if x minus 1 is smaller than 0, then let's have a look at this. The first sign is going to be negative, then this sign is going to be positive, then this is smaller than 0, but the negative sign will bring it back positive. Then we have positive, something that's overall positive, and then it's going to continue like this. So only the first term is negative, all the other ones are positive, okay? So in other words, the answer is no. So no, so we can't use the alternating series estimation theorem for this series on the interval from 0.5 to 1.5. But now I want to point out something. The problem is the left part of the interval. So that is the problem. If we were to evaluate at 1.5, this would be okay, right? What's causing the problem is really the numbers that are below 1. Okay, so basically when x is bigger than 1, you're okay, you can use that theorem. But when x is smaller than 1, you cannot use that theorem. So if the question was instead, can you use the alternating series estimation theorem to estimate ln of x for 1.5, then the answer would be yes, because 1.5 is greater than 1 and the series is alternating here. But if you're given an interval in which sometimes it's alternating and sometimes it's not, you cannot do anything about it. So I hope this is helpful. This completes the end of section exercise on section 11.11. Hope it was helpful. See you in class or in the next video.